In this unit, we consider circuits that include capacitors. The symbol of a capacitor is a parallel set of lines, which are intended to resemble the plates on a parallel plate capacitor. As we discussed in a previous unit, if we apply a voltage V across a capacitor of capacitance C, the charge Q on the capacitor is the capacitance multiplied by the voltage. Just as a single equivalent resistance can represent the effect of several individual resistors, we can find an equivalent capacitance to represent combinations of capacitors. Which of the following is true about these two capacitors? Correct. Denote the capacitance of one capacitor as C1 and the capacitance of the other as C2. In this arrangement, the left-hand plates of the two capacitors are connected and are therefore at the same voltage. The same applies to the right-hand plates. The voltage drop V across each capacitor is therefore the same. The charge on each capacitor is V multiplied by its capacitance. The total charge on the two capacitors is Q. The equivalent capacitance is this charge divided by the voltage. By using the equation for Q and canceling, we obtain the result that the equivalent capacitance is equal to the sum of C1 and C2. In general, the equivalent capacitance of multiple capacitors in parallel is equal to the sum of the individual capacitances. These two capacitors are in series. They have capacitances C1 and C2. A voltage V is applied across these two capacitors. Let V1 be the voltage across capacitor C1 and V2 be the voltage across capacitor C2. In each capacitor, the two plates hold equal and opposite charges. Consider the circled part of the circuit. Charges cannot travel into or off of this part of the circuit. Therefore, the net charge on this segment is 0. This implies that the charge on each capacitor is the same. According to the definition of capacitance, the charge Q is equal to the voltage V multiplied by the equivalent capacitance. The total voltage drop V is the sum of V1 and V2. The voltage across each of the capacitors is its charge divided by its capacitance. Combine these results as shown. The charge Q can be factored out. The inverse of the equivalent capacitance is equal to the sum of the inverses of the component capacitances. This can be generalized for any number of capacitors in series. Networks of capacitors can often be reduced to equivalent capacitances by combining elements in series and in parallel. If C1 is 2 microfarads, C2 is 3 microfarads, and C3 is 2 microfarads, what is the equivalent capacitance of the combination? Correct. Here is a circuit with a battery, a resistor, and a capacitor. The switch allows the battery to be included to the circuit as shown. The battery can also be removed from the circuit. Recall the voltage across a capacitor is the charge on the capacitor Q divided by its capacitance C. The voltage across the resistor is the current times the resistance. Let's suppose that the capacitor is fully discharged and the battery is connected. Apply the loop rule to this case. The direction assumed for any current is as indicated. We assume that the capacitor is discharged, that is, that Q is equal to 0. Therefore, a current equal to the EMF divided by the resistance flows through the resistor, as if the capacitor were not present. Because electric charge cannot cross the gap between the capacitor plates, charge accumulates on them. Note that the negative charge carriers move in the direction opposite that of the current. The positive charges on one capacitor plate represent the deficit of negative charge there. The voltage across the capacitor builds up. The current decreases as this charge increases, and eventually approaches a steady state. In this steady state, there is no current and therefore no voltage drop across the resistor. The EMF is balanced by the voltage across the capacitor. The charge on the capacitor is the capacitance multiplied by the EMF. Suppose the battery is disconnected and a circuit containing only the resistor and the capacitor is established. We can apply the loop rule to this situation. The voltage across the fully charged capacitor is equal to the EMF as we found previously. The sign convention for the direction of any current remains the same as shown. Solving this for the current, we find that its magnitude is the same as when the battery is first connected to the uncharged capacitor, but it is flowing in the opposite direction. The current is flowing in the direction opposite to that of the current arrow, I. The capacitor is now discharging through the resistor. Eventually, the capacitor will be fully discharged. The capacitor in the circuit shown has been fully charged by the battery and the switch has just been closed. What is the voltage change across the resistor in the indicated direction of I? Try again. Correct. This is a picture of an oscilloscope screen that is displaying voltage in a resistor-capacitor circuit as a function of time. An electronic switch repeatedly switches an EMF in the circuit on and off. We can derive the behavior of a resistor-capacitor, or RC, circuit as a function of time. First, we will consider the case of a capacitor being charged by a battery. Recall the equation for the voltages around the circuit. According to the definition of the electric current, the rate of change of the charge on the capacitor is equal to the current. Make this substitution in the equation for the voltages. This can be solved for the charge on the capacitor as a function of time. To see a detailed derivation of this equation, click on Show Derivation. If we divide both sides of this equation by C, we obtain the voltage across the capacitor as a function of time. Here is a plot of the voltage across the capacitor as a function of time. At time t equals 0, the moment the switch is closed, the voltage across the capacitor is 0. As time t becomes large, this voltage approaches the value of the EMF. The characteristic time required for the capacitor to charge, RC, is called the capacitive time constant. The voltage across the resistor decreases with time as the capacitor charges. This voltage is shown as a dashed line. The solution for the case of a discharging capacitor initially charged by an EMF of magnitude epsilon can be solved in a similar way. Click on the Show Derivation button to see the details. The solution for the voltage across the capacitor and a plot of the solution is shown here. A circuit contains a charged 5 microfarad capacitor and a 400 ohm resistor. How long will it take for the capacitor to lose 99% of its charge through the resistor? Correct. A circuit contains a 200 ohm resistor and a discharged capacitor. A 4-volt potential is suddenly applied, and the potential across the capacitor rises to 2 volts in 10 microseconds. What is the capacitance of the capacitor? Correct.